So welcome to the seminar. Today we have Hector Geffner with us. He is actually the first speaker from different continents to come to the seminar. That's one of the advantages of having it in virtual form. Hector is the ICREA research professor at UPF at the Universitat Pompeu Fabra in Barcelona, in Spain. He was born and grew up in Buenos Aires, Argentina, and obtained a PhD at UCLA under the supervision of Julia Pearl. He then worked at IBM Watson Research Center in New York, and then at Simón Bolívar in Caracas. Hector is a fellow of AAAI and EURAI, a board member of the European Association for AI, and a former associate editor of AI and JAR. He teaches logic and AI at UPF, where he has also introduced a course on social and technological change. And his most recent book with Blai Bonet is a concise introduction to models and methods for automated planning. He's also the recipient of an advanced ERC grant, a European research grant, to the research on symbolic representation for learning and planning. And today he'll talk about an updated version of a great talk he gave at HK, I think a couple years ago, on kind of combining System 1 and System 2 thinking, model-free and model-based AI. Welcome, Hector Geffner.
Okay, so thanks a lot for the introduction and for the invitation. As Fran said, so this part of it is based on a talk I gave a couple of years ago at ISHKA. So the idea of the talk is to provide a broader AI context for some of the recent work, okay, and machine learning, sort of, just to put it in a broader perspective within AI. So I'll talk a little bit about sort of some history of AI, about model-free learners, model-based solvers, and I'll draw some comparisons, okay, between these two learners and solvers in relation to System 1 and System 2, as Ferran said before. And then basically, okay, there is sort of some more recent work that I tried to bring in that has to do about how to get these two learners and solvers together, in particular the issue about how to learn automatically the type of models that the solvers need, okay, in order to operate. Okay, so this is the idea. So here we go. As I said before, I don't get to see too many faces. I don't know what I'm doing wrong, but in any case, so if you want to interrupt me, some clarification, so don't think twice, please do that, okay? So actually I did my PhD at UCLA, as Fran said, and at that time, it was very common to do AI by programming, okay? So some of you may remember Lisp, okay, or some even Prolog, okay, and at that time, AI programming courses were very, very important, and it was not unusual, even in the 80s, to do a dissertation in AI by picking up a chart map and some task, okay, so you figure out how to solve the task, maybe just understanding jokes, understanding stories and things like that, and then you write a program to capture the reasoning that goes in this task. So very, very interesting ideas came from this work, many interesting books, and actually one of my favorites books came from MIT in the 80s, is the structured interpretation of computer programs that was heavily influenced, okay, by this idea of AI programming and some of the programming languages developed in AI. But there was an important methodological problem, is that these programs that were written by hand were not sufficiently robust or general. So increasingly, as we move in the 80s, you can see in AI a methodological shift away from writing programs for ill-defined problems like understanding jokes, stories, and things like that, more towards designing algorithms for well-defined mathematical tasks, okay? And in particular, there are a couple of programs that I will be the focus of what I'm talking about that are learners and solvers. Both learners and solvers are special type of programs that have a very crisp functionality. They both map inputs into outputs by solving, okay, in the middle some mathematical problems. These solvers and learners are general as they are not built, okay, with certain type of examples in mind, but with certain mathematical models in mind. So I'm going to try to give more details about this idea of solvers and learners. Okay, most of you probably are familiar, especially with learners, to draw some contrast and some commonalities between them. So the idea basically in deep learning and in deep reinforcement learning is again to construct and to learn these functions that map inputs to outputs. The structure of these functions is given by the structure of a neural network where there are some adjustable parameters, and these parameters are learned by minimizing some error or function. Okay, so according to whether you use deep learning or some sort of deep reinforcement learning. So in the case of deep learning, the inputs may be an image and the outputs may be a label or a bounding box and things like that. In deep reinforcement learning, the input may be the configuration of the board, and the output may be the value of that particular configuration, the action that you should play in that particular configuration, or even the policy distribution of the actions that can be done in that configuration. So in any case, so the idea is that you use some version normally of gradient, stochastic gradient descent to adjust the parameters of this function whose structure is in the network. And once that you do the learning, okay, you have the function and you can easily map inputs into outputs, okay, to find, okay, the actions to be done in a given state, okay, or to find the distribution and so like that. We don't have to get into the details. So the main lesson is that these ideas are basically responsible for the prominence of AI in the news. So some true breakthroughs, okay, that have come out from this work in deep learning and deep reinforcement learning, like programs that like to play chess and checkers at world level, okay, by self-playing alone. The basic ideas that underlie some of these methods are not necessarily new, but doesn't take away any of the credit. So these are really among the most important accomplishments in the history, I would say, of AI. Of course, this does not mean that general AI or AI is around the corner. There are many, many limitations. And some of the limitations actually have to do about the type of input. So the type of inputs that these network states have a fixed size, okay? So this fixed size is fine when you want to play chess or play Go, but if you get into other type of problems, okay, that are common in AI, okay, so this imposes a limitation about representation, how to use these fixed input representations to represent things that in principle may have arbitrary size. So there's the paradoxical and ironic situation where maybe it's relatively easier to think about how to get something to work in chess, okay, that, let's say, to be able to deal with our beloved blocks world, we are trying to do arbitrary instances. On the other hand, we have solvers. So the solvers also map inputs into outputs. For instance, SAT solver takes instant of the SAT problem and map them into whether they're yes or no, according to whether the instance is satisfiable or not. A classical planner takes a classical planning instance and outputs, okay, a plan that solves that particular instance. In a Bayesian network, you may have a network and a query, and the output will be the answer to that query, and so on. So in these cases, okay, you get the inputs, you get the outputs, and there is no training that is needed. Instead, what you need is the model and the semantics of the model. Be SAT, be a classical planner, a Bayesian network, or whatever. Some of these models are very, very general, and they are not tailored to particular examples. Some of the models are extremely expressive, okay, including, okay, POMDPs that some people say, okay, are sort of very complete. In a way, okay, there is a way you can think even about learners as solvers are trying to solve a continuous optimization problem. Okay, you're trying to find the parameters that minimize a certain loss functions, and indeed some of the tools that we have, okay, for doing deep learning, okay, take this form. We are supposed to program the loss functions, to program the functions, and so on. And you have the algorithms, okay, that are trying to get approximations of these continuous optimization problem. In all cases, okay, so these problems for computing the outputs from the inputs is hard, again, be hard. And as I said before, the size of the inputs is not bounded. The challenge, okay, for people working, let's say, in SAT, classical planning, and all these various models, is to develop algorithms that will not necessarily break due to the number of variables in the problems, okay? Because they are models or problems that are very large in size, but not necessarily, okay, they are hard. So the challenge in some sense is to be able to handle those models that have a large number of variables without necessarily breaking down in the middle. It's useful to draw some comparisons and contrasts between learners and solvers. So in the case of the mapping, okay, that you obtain from learners, so basically you have a slow learning process. After the learning process, you get the function f itself in this picture. And then once that you get the function after the slow training, you can very easily map inputs into outputs. In the case of solvers, on the other hand, we never compute the function f itself. We compute the function f in a lazy way. For each given input, you compute the output. So in a sense, while for learners, so we have a slow training process to compute the function f, and then you can apply this function f very fast to any input. So you get outputs in the polynomial time in the science of the networks. In the case of solvers, the solver has to think a bit, okay, or sometimes more than a bit, in order to map the input into an output. So in some sense, it's the idea of thinking. You have to think, okay, for each individual input that you get, okay? So thinking is hard. Always make fun that it's not longer in fashion, apparently these days, okay? But somebody has to do it. And actually, it's feasible to do thinking and to do thinking effectively once that you have the right computational ideas, in the sense that many of the problems do not have to behave as the worst case scenarios, okay, envisioned by this complexity results. So what I'm going to try to do now is to focus on some of these ideas, okay, that have been developed in the area of planning, drawing a little bit of our own work. Some of these ideas, okay, I will be familiar to some of you, okay, some may be a bit more novel, then we move to some other things, okay. So one basic idea is coming from the 90s, actually, is about how to solve classical planning problems efficiently. So in a way, so classical planning is about finding paths connecting some initial node to some target node in a huge graph, a graph with the number of nodes that is exponential in the number of variables. So the question is how you solve these search problems in these huge spaces. And one of the ideas that becomes sort of a standard is a variation of an idea considered before by Polya, Minsky, Julia Perl, and so on, is that you take a compact representation of the problem, of the planning problem itself, and you relax this problem. You solve the relaxation of this problem, that is, you solve the simpler problem, and you use the cost, okay, of solving this simple problem as an heuristic for solving the original problem. In the case of classical planning, meaning planning when you have an initial state that is completely known and you have actions that are deterministic, the relaxation that is a standard is the so-called delete relaxation, or more generally the monotonic relaxation, where basically the effects on the actions is made monotonic. It means that you apply the action, certain things become false, certain things become true. In the monotonic relaxation, you forget about things becoming false. So you accumulate more and more atoms. This idea of monotonicity makes the relaxed problem decomposable and therefore tractable. Finding one solution, okay, for the monotonic relaxation can be done efficiently in low polynomial time, while the original problem, okay, is space complete. Okay, so you solve that problem and you use the cost of solving the relaxed problem as a heuristic for getting the search in the original problem, and this heuristic gives a sense of direction, okay, for doing the search. In this way, you can basically solve any problem from scratch. You do not need, as learners, experience on related problems. What you need is actually the model of the problem, and not actually any model. Okay, you need a model expressed in compact form, because otherwise this relaxation cannot be done if all what you have is a simulator. Okay, so there are some other ideas that work in those cases, not this type of a standard computational approach. Let's keep moving to illustrate a little bit of the ideas. Okay, another problem, okay, where you can see the difference between approaching the problem from the point of view of learning or from the point of view of solving or thinking, is goal recognition. In this case, as an illustration for, there is an agent that initially is at the location S in this grid, and it moves up twice. Okay, so the issue is to figure out whether he's trying to go to A, B, C, or any of the other letters that we see in these grids. Okay, this is basically the goal recognition problem. So in some sense, it's the inverse problem of planning. Here you have a pool of possible goals, and given the behavior that you observe, okay, in the agent, you're supposed to come up with a probability distribution about what is the true but hidden goal of the agent. In a sense, that's like a classification problem, so it's particularly appropriate for learning, because you're trying to classify the behavior that you observe in one of the classes that you have, in this case correspond to each one of the goals. But the problem, again, can be approached from scratch, given a model of the domain faced by the agent using planner. Okay, so basically the idea is, first of all, that you can express the posterior probability of the goals given the observation using a Bayes rule. Okay, so if we assume that we have the priors given, or the priors over the goals are uniform, the probability of the observation is a normalizing constant. So basically the key issue is how to find out the so-called likelihood, the probability of getting this observation, given that G is the true goal of the agent. Okay, or in other words, is how well each of the different goals or hypotheses predict these observations that are obtained. And the interesting issue is that you can map, okay, you can obtain, or you can define these likelihoods in terms of a monotonic function of two cost measures. What is the cost of achieving the goal with a plan that complies with the observation, and what is the cost of achieving the plan, okay, that achieves the particular goal G without complying with the observations. When you compute these two cost measures for each one of the goals, you can plug it into a very simple formula, actually a sigmoid, to get the likelihood, how well each one of the goals that you have in the pool predicts this set of observations. So at the end, what you get is that the posterior probabilities, okay, can be computed using Bayes rule, and 2 times the number of possible calls to the planner. Okay, so once again, so even though that this is a classification problem, you can solve this problem from scratch by doing this number of calls on the planner. Though no experience of related problems is required in order to do this problem. You're solving it by thinking, not by experience, okay, by using a model, okay, rather than the data. Just one last idea that I have to mention about planning is a very simple algorithms, okay, or very simple algorithms, so-called width-based algorithms, that have been found to be remarkably effective in certain settings in planning. Okay, so the simplest algorithm, okay, in this family is the so-called IW1 algorithm that basically takes a set of features, okay, as an input. Normally, in the case of planning, the set of Boolean features F is the set of atoms in the problem, set of ground atoms. Then IW1, the way it runs is extremely simple. It's a breadth first search that every time that you generate a state that does not make one of the features in the pool true for the first time in the search, okay, you prune the state, okay? That means you don't generate the children of that state. That means that if you have n features in the set of features, you're not going to be able to expand more than n states. So extremely simple algorithm, okay, and that actually does not need even a compact representation of the actions and variables and so on. And there is a version of this algorithm called IWK. The only difference with IW1 is that rather than taking the features, the individual features in F as the features that you use in the algorithm, you use conjunctions of up to K features. So one remarkable result, okay, of this very, very simple algorithm is that if you take most of the benchmark domains that people are considering planning, and we are talking about tens and tens of different domains, it turns out by running this algorithm with K equal to 2, okay, for the most part, you are able to achieve the single atomic goals of all these problems, okay? So this is pretty remarkable. If you take, most of these problems span exponential spaces, okay? So these algorithms, IW2, okay, running low polynomial time and will expand not an exponential number of states, but at most a quadratic number of states. So what this algorithm is showing that most of the plans, okay, for achieving these individual atoms, okay, so they lie in this particular subset of this exponential set, in this subset that can be reached with this algorithm. So this parameter that we use in some sense to characterize is something you can prove. It's not just an empirical observation. You can prove that in many of these domains, this algorithm, IW2, in certain cases IW3, okay, will be able to reach all the goals in the problem, all the individual goals. So the joint goals, okay, will have what we call sort of a larger width, and normally you can approach them with using this sort of algorithms along with some different serialization method. So one advantage of these algorithms in comparison with standard planning algorithms, as the one that I mentioned before, based on heuristic search, is that you do not need a compact representation of the actions. All what you need is just the structure of the state. So what are the variables, and what are the variables of the values of the variables in the state. Actually, these algorithms do not even take into account the goal, except to detect that is when you hit the goal with the nose, okay? So in that case, sometimes it's not a search that is oriented by the goal. So these are truly exploratory algorithms, okay? That you happen to find the goal when you, so in some sense, you can even just work with the goal procedure, okay? That tests whether a state is a goal and so on. Again, you don't need a declarative representation of the goal either. One interesting outcome of this work is that there is a variant of this width-based algorithm that basically have shown that you can do planning even on the standard PDDL benchmarks using an algorithm that doesn't look at the structure of the actions at all. Means that I take the actions, I compile them in the procedure that give me just what is the successor state that I will do an action in the state. With this information, it's much poorer what normally have. You can get a planner on the standard PDDL benchmarks works as well as the standard methods. Another variant we use to do online planning, okay, in the Atari games directly from the screen pixels, basically almost in real time. And one interesting thing is once that you run this algorithm in the case of the Atari games, you get scores that are almost as good as the one that you get with the original DQN learner, okay, that basically made a big splash a few years back. It's interesting again to see, okay, the difference between these two methods. So the DQL learner that does deep reinforcement learning, so requires sort of slow training, and after that, okay, you get the controller that you can apply it very, very fast. On the other hand, this other algorithm, rollout IW1, is thinking what to do by doing a limited look ahead, okay, almost in real time, each time that it moves. So once again, is the characteristic that we mentioned before about learners and solvers. So learners, you do slow training on related experience, and then you get the function that can be applied very fast. In the case of solvers, okay, they work right out of the box given the models, but they need to think, okay, a little bit for each input that they are given. I also like to draw a comparison. Sorry, I think I skipped this one. I also like always to draw a comparison between learners and solvers and ideas of system 1 and system 2. that have been pioneered by Danny Kahneman, and he actually, with Amos Tversky, he worked on the idea of heuristic and biases and cognitive processing, and he popularized these ideas. He got the Nobel Prize in Economics a few years ago in this book, Thinking Fast and Slow. The names of System 1 and System 2, however, are not his. They are from Keith Stanovich, okay, that actually wrote a very interesting book as well, okay, called The Robot Rebellion, okay, from 2005. If you liked The Selfish Gene by Richard Dawkins, and you like Thinking Fast and Slow of Danny Kahneman, definitely you should take a look at this book, because in a sense it's a marriage between these two things. By the way, the robot that is rebelling in the title is us, okay? It's humans. It's humans that are rebelling against. And for that, his argument is that we need system 2, okay? Because system 1 will not give us the freedom to pursue the goals that we want. A little bit in more detail, so the idea of system 1, that is the intuitive mind, system 2 is the analytical mind. So system 1 is fast, associative, doesn't take any effort, it's parallel, and so on. In some sense, you can relate it to the boxes that you get out of the learners. On the other hand, system 2 is slow, takes effort, is conscious, okay, requires attention, requires memory, and so on. So it takes much of an effort, okay, to do this sort of deliberate thinking, and this is why, okay, so many environments in life today, they try to play with our system 1, okay, because it's easier to manipulate that normally well-engaged system 2. I'm gonna come back to this issue later on, okay, so I'm doing well with time, so let's move on. Okay, so the key difference in my view between these dual accounts of the lives of the mind in terms of system 1 and system 2, what happens in AI between learners and solvers, is that in the human mind, system 1 and system 2 are extremely tightly coupled. Okay, one is calling the other all the time. You read a sentence, you're driving, in all these cases, you can basically need the two. And it's very hard to get a robust system by just system 1 alone. Normally, I would say that one of the reasons that I don't think we're gonna see self-driving car in normal cities anytime soon is because they are system 1 boxes. And sometimes, okay, you get things that do not correspond to a particular piece of experience that you have had, and you have to understand and think about that. Okay, so in human life, okay, we get these two systems, okay, calling each other all the time. This is something that is missing in AI, and this raises a lot of challenges. One challenge, okay, that I've been looking at, okay, and I'm aware that some of you have been looking at as well, is how to learn from data the type of models that solvers use and normally are written by hand, okay? So most of the planners, like classical planners, they use all these PDDL encoders, but these PDDL encoders are written by hand by someone. That is a huge bottleneck. So the question is, can we learn the different type of model representations used by the different solvers can then be learned by data so that they don't have to be built by hand? And this involves learning the symbols, learning state variables, learning useful features and abstractions, and in particular, if you want really good reusability, is to learn what we in logic call first order models, some of people call lifted models, where basically are organized around the idea of relations and objects, okay? So in the case of planning, we can think about basically 2 dimensions for doing representation learning from planning in terms of what are the inputs that you have and what is what you want to produce. In terms of what are the inputs that you may have, you can do learning from symbolic information, okay? So you have an image, somebody passes the image, and you get a symbolic representation of the image, okay, that would be like a symbolic input. Or you may want to deal with an input that is non-symbolic, like the image itself. There is a third option is in some sense the least informative or all what I will call black box states, okay? All what you know is that these two states are different, but you have no idea what is in one state and what is on the other state, okay? All what you know that these two states are different. So it's a bit less information what you get in an image, okay? These two images may be different, but the idea is that you're gonna pay attention to the content of the image. In the case of black box states, all what you know is that these two states are different. That's the only thing that you know. And also the second dimension is this input information is going to be used for what? Okay, you want to infer a controller, okay, model free, or you want to learn a model, in certain cases, a first order model so that you can do planning and generalization, okay, when the set of objects and configurations change. Or, okay, some other dimension that I'm adding here is the notion of a generalized model, where you're trying to learn a model that will help you not just to come up with a plan for a particular instance, but will work for many, many different instances. So what some people in planning these days call generalized planning. So what I'm gonna do next, okay, maybe I have 10 minutes I'll take, okay, is to address 2 points in this 2D space, okay, from this set of inputs and this set of outputs. So I'll try to talk a little bit about some of our recent work, okay, that is related to this idea in order to integrate learners and solver, okay, to try to focus on how to use learners to learn the models that are used by solvers and in particular by planning. So I'll focus on first, how to learn first order symbolic action models, okay, if you want lifted action models of the type that you have in PDDL, okay, that have the advantage that can be used, okay, regardless of the number of configuration of objects. And in that case, we're gonna take the inputs black box state, as I mentioned before. So the second point that I'm going to try to address in this space is how to learn generalized planning model from ones that you learn the symbolic action models as in the first part. By the way, there are many other works, okay, that added some other points, okay, in this 2D. Most, I would say, most work in deep reinforcement learning sort of address so the issue of when you have symbolic or non-symbolic inputs, and normally what you get in the output is the model-free control. I'm aware, however, that in some of your labs, some of the work done by Leslie, Tomas, Josh, and some of the students, okay, they're also addressing some of the other points in this 2D, okay? So that there will be some relation to what I'm gonna be saying. So let's start with the first part, okay? Those of you familiar with the standard language that you use in planning, PDDL, you don't need to understand the details, but the idea is that every planning problem, okay, is given as a pair, actually as a pair of files. On the one hand, you have the domain or the domain file, that is a first order domain where you have the action schemas and the relations. On the other hand, normally in case of PDDL, it's a different file. Okay, you have a file that provides the instance information, meaning the objects, sometimes the types, and the relations that they satisfy. From a logical point of view, basically the instance information is a set of grounded atoms, okay? The importance of this representation has to do with the notion of reusability and compositionality, okay? That are sort of two targets and two desires that we will have in terms of learning. So once that you get these first order domains, okay, you can reuse them, okay, when the set of objects changes, the number of objects changes. And the idea of compositionality is that you can express any sort of goal, any combination of goals as well. Okay, so the issue is how to learn, in some sense, these first order representation in terms of relations and action schemes and so on from data. The data that we care about is state graphs, okay? So we all know, so a planning instance P defines a state graph, okay? You have an initial state, you start applying actions and you get different states. And as long as you can tell one state apart from the others, what you get as a result is normally a finite graph. So the question that we have addressed, okay, with the colleague Bly is, can we learn the first order representation of a planning problem P, in particular the domain that is what we care, the domain D? Can we learn it back from the graph? So somebody gives you the graph. Can you get back okay, the first order representation of the domain. And a slightly more general setting is if somebody gives us different graphs. So you take blocks world, you give me the graph for 3 blocks, you give me the graph for 4 blocks, and so on. Can I learn the planning instance, the PI, okay, that correspond to this graph? That what they have is they all share the same domain. So we're trying to learn action schemas and relation from the graph, and basically from scratch, in the sense that we're learning the symbols and the relation, and we're going to detect the objects without having any symbolic representation at all to start with. Okay, we don't have a vocabulary, we don't have the relations, we don't have the predicates. Okay, we are basically the only inputs that we have are these graphs. Once that you learn the domain, that in principle you can use them to do planning over other instances. So the question is, can we do this? And the question is, how? Okay, so let's look at some examples, okay, of this. So the idea, for instance, in Hanoi, somebody gives you the state space of Hanoi, the structure of the state space. So in this case, this is the Hanoi state space for 3 disks. So the question is, can we learn, so the first order representation, in this case, basically domain contains a single action, okay, moving one disk, okay, from a certain peg to another peg and so on. And actually what we show here at the bottom is the first order representation that we learn. Of course, the names that we choose for these things, like this larger than another, to this not being equal, okay, some this being clear and so on. So we are choosing names, okay, in terms of what's happening with the interpretation that we get, okay. What you get, of course, are arbitrary names, but basically this is the schema that we get. So the names are used to convey the meaning of these representations. Okay, for the approach that we pursue, okay, so this is another problem, okay, so the picture shows the state space for a gripper problem. Gripper problem means that a bunch of packages in one room, and you're supposed to take these packages to another room using a gripper of different capacities. So maybe the gripper can handle 2 packages at a time, 1, 3, and so on. And in this case, the input graph is labeled. So we are using 3 labels. So we distinguish when you do a move, when you do a drop, and when you do a pick. In any case, the number of labels in these graphs, in the first case was 1, okay? Every edge had the same label. Here we use up to these 3 labels, a constant number of labels that's independent of the graph size. And once again, okay, we get the representation that is shown here on the left, of course, with the names of the symbols, okay, that learn, okay, with names that we can sort of recognize. So the issue is how we formulate and solve this problem. Actually, so the task I already mentioned is basically we're interested in finding the simplest instances, okay, PI from I1 to K that share the same domain. You have no idea, you do not anything about the domain. Each instance have different instance information, and you are supposed to learn this from a set of graphs enabled. Somebody is giving you these graphs that we assume to be complete, okay? There are ways to extend them when the graphs that you are given in the inputs are not complete, but this is actually sort of crisper and simpler. The thing to notice, again, is that we have a very crisp and clear target language, okay, for the representation that we want, okay? We want, in some sense, to learn these type of structured representations that are first order, and we also know, okay, that we can introduce a number of parameters. So how many action schemas, okay, how many predicates, how many, what is the arities of the different predicates that you have, of the action schemas that you have. And normally every domain can be characterized in terms of a number of small values of a small number of parameters. So once that you add these bounds, okay, in some sense this will be like hyperparameters, okay, and you fix the value of these hyperparameters to find whether there is domain representation that complies with these bounds together with some instance information that will generate the graphs that you're given in the input becomes a combinatorial problem. And in this case, and this result that I showed before about the graphs, okay, we address this combinatorial problem using SAT solvers. So we encode this problem of finding these representation as the SAT problems, and we learn these representation from the SAT solvers. So more details you can get from this paper that you can find in the archive, learning the first order symbolic representation from the structure of the state-based space with Blythe. Okay, actually here is the way that the one instance of blocks world looks like. Okay, and again, this will be the output that you get. Okay, with the names for the symbols. Okay, that in some sense give the meaning that we found. If you're gonna see that this is not exactly the type of domain that normally you will write, okay, there are symbols like, for instance, one predicate means, okay, that the block is not in the table or are different and things like that. If you look at n table and so on, so in some sense it's a very convoluted meaning, but this is basically what you get, and the domain that you get is correct. So we learned this representation from, I think, 4 blocks, and this representation is good and will generate this space for any number of blocks. Okay, that's the way that it generalizes. So let me move to another point in this space that I mentioned before. So this is getting a bit technical. So the idea is that you do not have to follow all the details, just the idea. So what we are looking, so what is the output of you're trying to compute? What are the inputs, and some idea about the methods that will take from the input to the output. In case of more details, of course, you can ask me questions, okay, here, or you can take a look at some of the papers that normally include in the slides. So the second issue about learning models, about learning generalized models. That means models that will help you come up with plans that will not only solve one instance, that will solve a collection of instances, okay? Normally what they are called strategies, okay? So for instance, I want a strategy, a policy, or a general plan that will solve the problem of getting some block X on top of some block Y in any block world instance. It doesn't matter the initial configuration, it doesn't matter the number of blocks. All I care, if there is a block called X in the problem, there is a block called Y, no matter where they are located, how many blocks, I want, in some sense, the general strategy that will give me, okay, this goal. Okay, for us, it's relatively easy to come with these strategies. We're trying to do the same, okay, with our methods. We want to be able to come up with the strategies that look so easy for us to do. So when you're trying to solve blocks, you not only come up with a solution to particular instances, but it's very easy for us to come up with a general strategy. The way we deal with this problem, so the formulation, the language for the model is no longer the language of PDDL, so we are looking for a different type of language, okay, for these generalized models that we call qualitative numerical planning problems. The details do not matter too much. Based in these QNPs, they can be thought as propositional planning problems, like in strips with no variables, except that you have numbers, and these numbers can be decreased or can be increased qualitatively, meaning you don't keep track of the exact value of these numbers, you only check whether the number has become 0 or not. Why to do this sort of relaxation? Why not to keep track of the numbers themselves? Because numerical planning, even in the simplest setting, is undecidable, okay? So qualitative numerical planning, on the other hand, not only is decidable, there is a fragment that actually can be compiled in polynomial time into what people in planning call fully observable non-deterministic planning, form planning, that is very much like shortest path or MDPs, where you're trying to reach the goal of an MDP with a goal with probability 1. So the language that you use for this task is how to learn these general strategies. Is we learn, okay, from the data, we learn this generalized model expressed as a QNP, that means as an strips problem extended with these numbers that can be increased and decreased qualitatively, and then we know how to solve these models and get a policy that will provide us with a general strategy. However, in order to do that, in some sense, we are learning a language, a new language for expressing the policies from the language that is given for expressing the actions. So the key issue is how to learn the right actions, okay, and the right variables in this abstraction, okay? So I'm not gonna get into details, but at the end, we are solving this problem as well. Actually, in this case, the formulation, I would say, is pretty elegant and pretty concise, okay? It's basically a reduction again to SAT. In this reduction to SAT, the set of formulas that we need, basically, we take as inputs a set of sample transitions. We know the primitive predicates of the domain. So we know the representation of the action. So we know on, we know clear, we know these predicates that are given in the case of blocks, and we have a fixed grammar that allows us to generate more predicates, derived predicates after the primitive ones that we have. The CNF formula that is fed to the SAT solver so takes into account this set of sample transitions and this pool of possible features. Okay, the SAT encoding then uses these three types of variables. So basically, for each possible feature, you have a Boolean. Is this feature the one that I want? Is the one that is selected? It's not. And then two other sort of atoms, D1 and D2 atoms, one that establishes a distinction between two states, so S and T are two states, and S prime is a transition, T prime is a transition as well. So basically, these are the only atoms that we need, and only 4 types of formulas, okay, that basically lay the distinction, okay, among states and among transition in terms of these selected features from the pool. And the key axioms, okay, in this formulation are the bottom 2, okay? The last one is simple. I want to be able to select features that distinguish states that are goal states for those that are not, okay? The third formula in the list is slightly more complicated to explain, so I'll skip it, okay? But there is a property that you can show about the encoding and the type of model that you get out of this encoding. Okay, just to make the story short and to give an example again of the input and the output. Okay, so here is about the example. So we want to have a general strategy for solving block X on top of block Y, no matter the number of blocks, no matter the initial configuration of the blocks. So the data that we use are 3 strips instances, very small, I think, with 4 and 5 blocks, okay? So the number of state transitions in this instance is a few hundred, okay? The number of features that are generated from these primitive predicates are basically a few hundred as well. And once that you feed these formulas into the SAT solvers, what you get are the features and the actions that I'm showing here in the slide. So actually you get 5 features. 3 of these features that you get are Boolean, okay? So whether X is being held, some other block is being held, whether the goal has been achieved or not, and 2 numerical variables, N, X, and Y, that basically count the number of blocks above X and above Y, and are decremented or incremented qualitatively in the actions that are learned. So here again, so are the actions that you can see. Once again, the name of the actions, okay, are names that were given to these actions that are discovered as part of the SAT encoding. And what you see at the bottom is basically the policy that is obtained by solving the resulting abstraction with an off-the-shelf fault planner, okay? So there is basically, this is the policy that you get, and you can actually prove that this policy will work, okay, for the range of problems that we got. So again, so the details, no matter, of course, you can be happy to answer questions, but the point, as I mentioned before, is trying to bridge a little bit the gap between the solvers on the one hand, the learners, and you use learning methods, okay, in many cases based on logic, especially the inputs are not images and things like that, in order to get models, and in this case, generalized models. So okay, I'm gonna start trying to wrap up, okay, some of the main lessons. Okay, so first point is true breakthroughs, okay, in deep learning and deep reinforcement learning in the last few years. second point is there is an interesting parallel between the boxes that you get out of the model-free learners and the thinking that you get in model solvers and the so-called system 1 and system 2 in the dual accounts of the human mind. From this perspective, okay, normally one is thinking about, so what are the limitations, okay, of deep learning and deep reinforcement learning, is that basically deliver boxes that comply with system 1 only, okay? Another way to say, of course, is, so it's the difficulty of dealing with problems that are out of the distribution, but they're just another name to saying the problems are new problems and you have to think about them. So from my perspective, and I think for many others, one of the main challenges, okay, that we face in AI is to be able to build systems that combine the system 1 and system 2 abilities. That means that combine the abilities of learners and the abilities of solver. One of the problems, okay, that arise from these challenges is learn automatically from data the type of models that people write by hand, okay, when they use solvers. Okay, so I mentioned about these 2 dimensions, okay, to illustrate some of the points in this space that we deal with, okay, some other people as well, okay, symbolic, non-symbolic, and black box states used for model-free control, model-based on this idea of generalized model. So that's basically the main technical points, okay, that I wanted to use. I'll make one commercial and one final slide. So I'm doing with time for Ran, so I can take another minute.
Maybe a couple of more minutes, but yeah.
Okay, good. Couple more minutes. Okay, again, I don't get to see many faces. I hope that some of you are still around, okay? First, the commercial. I think that Ferran was very kind to mention about these ERC. These are ERC grants, are very large grants in Europe and so on. So this is just a commercial, okay? So if you know about people interested in this type of ideas about how to do representation learning for plan and things like that, okay, I'll have to figure out what I'm gonna do with all this money. So I'm gonna be hiring, okay, a number of people, okay? So please spread that news. Normally, when I give talks in AI these days, AI appears so much in the media and so much everything, and many people saying that AI will solve everything, okay, from the better world and the coronavirus and so on. I just want one slide to show my skepticism about some of these claims, okay? And since I'm talking about system 1 and system 2, just to emphasize that system 2 is not just necessary for AI systems, okay? System 2 is essential for people and especially for societies, because system 2 is basically a social process. That's a way that we learn to reason and so on. AI is far from human level intelligent, but as it is, still can be used for good or for ill. So in my perspective, ethical committees, AI principles, the Silomar principles are good, okay, but they are not sufficient, okay? So we live in times, okay, where there are very strong forces in the markets and politics that keep playing with our system 1, normally focused, okay, on the bottom line. So the point that is that if, from my perspective, if we want good AI, we need actually good and decent society that uses, okay, actively as the system 2 and that cares about the common good as well. Sometimes when I'm more ironic, okay, the line that I is the one at the bottom, we need artificial intelligence for the social good because natural intelligence is busy in other pursuits, okay? So thanks a lot.
Cool. We have time for a couple of questions.
I have a question. So thanks, Hector. That was good, and I was here. And I'm inserting myself because also I have to run to another meeting. All I do is run from meeting to meeting while sitting in my chair. I was interested in the work on inducing the first order model from black box states. I read that paper recently, actually. And what I was wondering is really, when is it that you could ever acquire that data? It seems like in a real problem, these kind of high-level symbolic structures, they're very useful, but they're almost always an abstraction of some actual low-level system that's executing motor torques or something to pick up the objects. And so it seems to me that the difficulty is actually in constructing that discretization, and that if you're constructing that discretization from a real world, then you might have access, then you'll have access to more than the black box states. So I'm curious about the setting that you imagine that happening in.
Yes, so I tend to think that in the type of settings, okay, let's say for example robotics, okay, one problem of the approach will be that the target language that we use, this sort of PTDL type language that we learn, is actually not too adequate, okay, for those settings. And this is actually one of the reasons that normally it's a lot of work to use this type of ideas in planning when you're trying to do task and motion robotics, as you know pretty well. So you have to add a number of other things, okay, to make these sort of a suitable language for expressing these problems. So I will say that in those cases, and many other cases, for sure, okay, you need other target languages. So this is just one particular type of target language. Even in the case, if you ask me, for instance, even about other problems that are discrete, okay, let's say, for instance, I want to learn a first order model of the Atari games, or even Breakout, or Pong, or things like that. I would not say that these are good languages. These are not good languages because people cannot model those problems in these languages. So in that sense, I tend to think that for those other problems you need to build, in some sense, you want to learn languages that are good for modeling those problems. So in some sense, if you have a good language for modeling the type of problems that you have in mind for task and motion and so on, okay, so they will be to learn those languages. Definitely, I don't think that this particular type of language. There is another limitation, okay, about this. What we do here is we are learning the language. So we learn the schemas, okay, but we do not learn to ground the predicates in the schemas, okay? We only know how to ground the predicates in the schemas in the training data. But if somebody wants to give me another problem, in some sense, these other problems have to be expressed with the predicates that we want. So in some sense, so we are splitting the problem of learning the representation in two parts. Learning the representation itself and learning how to ground the representation. When people do the learning and so on, they learn the two things at the same time. So we are splitting the problem in two, and not only that, we are only learning the first half. We are sort of doing work trying to do the other part as well, okay, both in this type of models and the ones that I mentioned about QNPs, but that's a piece that is missing, okay, in some sense. Just learning the language or the schemas. It's so how to provide a new instance, so somebody has to express that instance by hand still. Mm-hmm.
I see. Yeah. Okay, thank you.
Sure.
Are there other questions?
I can ask one. This is Tomas. One that I'm interested about the IW bound, the fact that most of the problems you run across, you can solve with IW2. To what extent is that a property of the competition domains of handwritten PDDL versus likely to be a property of real problems?
Well, it's hard to say. I tend to think, okay, I will not say that the fact that this problem have a low width, okay, from the point of view of the atomic goals, I will not say so much that it's a representation, it's a property of the domains chosen, but it's a property of the representation used to solve these problems. In other words, if you give me an instance of the blocks wall and you remove the clear predicate, okay, this will have an effect on the width of the problem, what we get. So my take on your question will be that low width property is a desirable feature of the good representation, okay? Now, there are certain problems where it's impossible to have a low-width representation, especially puzzles. So the problem, for instance, of moving the larger disk in the largest disk in a Tower of Hanoi from one peg to another peg, okay? So the width of that sub-problem is not bounded. It grows with the number of disks because it's a domain we have to do and undo actions many, many times. Okay, but in the case, even in case of blocks, I would always say that most of the problems are relatively simple, okay, in the right representation. And one property I will say of this representation is this property, okay? But so we...
Because, I mean, you have to think very hard to come up with a block swirl that's as simple as the one that's in Padilla, right? It doesn't capture many of the features of the real world, right? It's only one block on top of another. There's no interference in reaching the blocks, and so.
Good. For instance, good. That's an excellent point. But let's say that do block swirl, and you have two types of blocks. You have large blocks and small blocks, and you can place as many small blocks on top of a large block. Okay, so you can have 10 little blocks on top of a large block. In that case, actually, that problem doesn't have, so it depends on the way that you represent the problem. You're going to get a bounded width for that encoding or not. So in some sense, part is a property of the encoding. It's not necessarily a property of the task itself, even though I dare to think that there's some tasks that cannot be represented in any way that will give you a low bounded width.
Yeah, I mean, that's my guess. But it's a good observation that it has to do with encoding. Yes, thank you.